So welcome back everyone. Today is our 5th lecture in analysis of algorithms. So today will be probably the only lecture where we will do very little coding in general. This is maybe a little more mathematical, more theoretical, but the main goal today is to learn the master method. Alright, so we have some idea of big O notation. We'll cover the basics, we'll go over big O notation again. Then we'll get to this master method. So what's master method all about? It is about finding big O complexity in recurrent relations. And what's recurrent relations? Basically, well, when we see recursion, that's where we usually have a recurrence, basically. So, all right, so let's review the big O notation. And again, maybe a little bit more formally. So, in this picture, you can see this over here, right? Yeah. Okay. Yeah. Right. We have this is from Wikipedia, of course, but you have a growth function. You have some function, the blue one. Right, that's the blue one, right? On f(x) is our function, right? So what the big O notation is really saying, at some moment at some x could be very large, right? We can find a c, right? We can find a constant. Right? Could be 5,000, could be 3, could be 6,000, right? At which moment our function is always going to lose. When I say lose, meaning y is going to be always less, right? Forever, basically. That's always what I'm saying, basically, right? At some moment, this growth function is going to dominate our function, right? It's going to always win, basically. It's going to have y larger. So basically, that's what we're saying. Basically, our function is no worse, right? In the worst case scenario, this function, right? We are below this function, basically, right? So that's when I say O big O notation, right? When I use big O notation, I say something is O n squared. I'm saying worst case scenario, right? Then we'll get the n squared complexity, right? Worst case scenario, right? So that's why when we see here, right, worst case scenario, we use big O, right? Well, the thing is, of course, in practical sense, big O is easy to write. Right? It's very commonly used in general, right? It's the most used of these complexity terms. But turns out there's more precise ones as well. There's omega and theta, right? This is theta, right? So when we say something is big O n squared, right? We say, okay, in the worst case scenario, it's gonna be no worse than n squared. So when somebody asks you, what's big O notation? Big O complexity of, say, bubble sort. What answer would you give them? Bubble sort.
N squared.
N squared, okay. But if somebody gives you answer, oh, it's n cubed. Well?
They're stupid.
Well, you can say they're stupid, but they are not technically incorrect. They have said the correct answer. They have said it's bubble sort is n factorial. And technically, they are correct. The best type of correct is technically correct, right? But so, because the function, again, worst case scenario, right? The n factorial is going to dominate, right? When we go back to this function, right? It could be something much more faster growing, right? N cubed, n to the fourth, n to the fifth, right? It's just the thing is, it's stupid. You're right, it's stupid because it's useless, basically, right? This information, yeah. If I say pretty much every algorithm is, O n factorial, right? It's technically correct, basically, correct saying, but it doesn't really help us at all, right? We usually want the tightest, like the one which is the closest, right? Because that's why we usually what we want, because it's most useful, right? Otherwise, it's just, hey, I can say, oh yeah, merge sort is n to the fifth, right? Yeah, it's correct saying, but it's really useless, right? So that's why big O, you have to be a little bit careful with big O notation a little bit, right? You can. If you're in a job interview and somebody asks you what's complexity, you can say it's n to the fourth, right? But they say that's wrong. It's not wrong. It's just useless, right? Difference, right? So now we get to the other two, right? So let's look at the merge sort, right? So merge sort in the way is kind of easiest because you see average is always n log n, right? We always do n log n operations, and also in a base case scenario, right? So now you hopefully can get the omega when you see omega notation. And it's again, in practice, if you look at some paper, it's much less used, so it's very, very useful. Omega means the lower, the best bound. So basically, let me do some paint. I've been itching to do some paint here, so you guys will see some nice paint. All right. I want to draw some. All right. So we'll have our function. What color are we going to use for our function? This is going to be x, of course y, right? Right. It's like plus, I don't know, plus to, I don't know, 1,000. You know, I don't know, something plus, you know, plus 100, right, or something, right? You know, 1, right? And now let's do our function. Let's do a function in what color? Green? No, green would be growth. Our function would be red or orange, right? Our function goes like this. At some point, like something like this. Well, I don't know, right? But right, that's our function. That's going to be f, right? F to x, right? And basically, we want to make some statements about it, right? So when I say I'll use green for omega, so this is going to be the green. So our green function, something like this, right? And at some point, right, it goes like this, right? So basically, right? So this is our growth function. I can't spell. Where's my G? Where is it? I lost my mouse. Oh, here you go. Gonna see. So growth function, right? G, right, x. And I guess to be correct, do we put the C here or do we put the C here? I think technically, yeah, you put C afterwards, right? So you put C afterwards, right? Some constant. Again, it could be very large. So C could be maybe, you know, pick any number, right? So so this is going to lead us to O, right? This is for the O, right? O GX basically, right? O GX basically, right? Okay. So similarly, what color are we going to do for lower brown? Let's do it violet. No, what's violet? That's purple. Sorry. So again, it's possible. It's purple is somewhere here, right? But still here. But basically, eventually, right? It's here basically. And that's going to be our other function, basically. I guess I'll use h, right? Well, h, right? X, right? And again, same thing, right? Another constant. So obviously, you pick the lower constant. So that's a trig constant, right? So I did this. Why is this is like really abstract, right? Remember, I'll give you maybe more concrete example, right? Let's imagine. Very common is let's say n squared. Let's say n squared minus n, right? Right? Something like this. For example, right? And I know students usually have saying, okay, this is less than n squared, right? But no, this part here, I'll say, you know, minus to, I don't know, minus to 5,000, maybe 500, right? Minus 500, right? Something like that, right? But still, we can find at some moment in time, we can find n squared, right? Green one, right? You can find n green, right? N green, right? N squared, right? Dominant, the dominant one, right here, right? Yeah. So that's what going to be our growth function, right? And we can find something like, I don't know, 5,000 or something at some moment. This part here is not going to pay attention. So at which moment, I think probably 1,000. Probably 1,000 at let's say maybe like 2,000 or something. I don't know, 2,000, right? C, right? This part here, right? And again, I'm not doing the math. Maybe I'm wrong. I think 2,000 should be enough, right? So that's the thing. We have big freedom, a lot of freedom to pick, right? And at the same time, well, C looks like it's gonna it start working immediately, right? Here we can pick maybe, I don't know, 0.1 or something, right? Maybe we can pick it's always at some moment. Let's say you can put probably just for here you can do purple. Probably just 1 is fine. You know, 0.1, right? Again, n squared, right? So this is omega. Yeah. So this is omega. But this, right? When we can, in this case, n squared and n squared matches, right? So when big O and omega match, well, it's a very tight bound, right? Basically, squeeze from both sides, right? We can find the big C in upper, small c in the lower, right? And we can squeeze and we get theta. So we can also, in this particular case, I can say it's theta, right? Theta. I don't know. I don't know how to spell. horrible, right? N squared, right? Theta. Right, my amazing photo of my paint skills. Theta. Theta. I need a better mouse here. Okay, right. So omega, right? Okay. So hopefully this is what basically this is what they're talking about, right? Again, it's not a precise exact function definition or something like that. We're just trying to say, okay, roughly where the bounds are at some moment, right? So, and again, why should we use this at all, right? So, because it's useful, right? Again, like I say in statistics, all models are wrong, some are useful, right? And here too, right? This is a useful tool, right? It's a very rough approximation, and again, you say, okay, something n squared, right? Usually we say, big O n squared. Usually, actually, people talk, everyday usage, they talk about theta. It's a typo. The average here, right? This part here, right? This is what usually is the most important one. Of course, worst case scenarios too. The best case scenario is seldom that useful, right? You rarely get the best case scenario, right? So we care about the upper bound, right? And again, it could be, remember, in this case, I hope you can agree with me, I can put n to the cube, n to the fourth, and so on, right? It's just not very useful. But the thing is, now here's the point, I cannot put n to the 1.9 or n to the 1.9, n to 1.5, right? Because that is, at some point, I cannot find a constant then, right? Because this is going to be at some moment, right? N squared is the lowest I can go. So n squared is the lowest I can go if my own function has n squared inside, right? Do you guys follow this idea? At least, roughly. Okay, so that's basic background. Hopefully this picture helps. If not, I'll see if I can make a better one. So then we'll talk about their slides from MIT, right? The big book of algorithms, right? And it's a little bit more, of course, heavier than what I use. So how do we solve this, right? So when we have a recursion, right? We have a definition. We define the problem. How? In recursion, how do we define the problem? In terms of itself, right? So yeah, smaller version of the problem, right? So, of course, if you define a problem with the same size as your problem before, you have infinite loop, right? So you have to always go down somewhat, right? But the thing is, what might not be useful, what might not be obvious is how do we say, okay, we have recurrence here. This is the third slide. We have this recurrence, right? Tn. So for each, this is an integer multiplication algorithm. Don't have to worry about, don't have to learn. Let the MIT guys do that, right? But it's a way of, if you're interested, you can read up on it. But basic idea is it's a faster way of multiplying integers. But yeah, so for each original size of n, right, you have four instances of half the size. Well, and plus, for some reason they give you 100 n class, and 100 n, right? It doesn't say here. It's just okay. It's just a random example, basically. So, but how the heck do you solve this, right? So what is complexity, right? If you have a function, right? If you have a loop-based solution, right? You can count the loops and you can get the idea, right? And go down, right? If it's a loop within a loop, it's n squared, right? No way, and of course, if the loop invariant is n, of course, right? Because both times it's based on n, of course, right? So, but for recurrence, how do we solve this type of thing? Well, on the worst way to do it is use something called substitution method, basically. And again, so I'll show you the idea, but it's basically, I'll skip ahead. You don't have to use it, basically, right? You could, theoretically, if you do not know about master method, right? So that's why I don't want to scare you a little bit, right? So basically, you guess, and that's the worst part, right? You have to guess. First you have to say, okay, what's the complexity of this, right? You could say, oh, it's O(n) cubed, right? So, again, I said it could be completely useless statement, right? I mean, it could be somewhat useful, but might not be a precise statement, right? Because it could be n to the fifth also. Okay, so we assume we guess it's n to the cube, right? And then remember, we have to find at some point, right? So this means that there is some c at some point, right, where we are going to lose to k3, right? Or recurrence is going to lose to this basically, right? At some point there's some c, right? So c basically any number, right? Any constant number, right? So we have to prove by induction, right? And I don't know how many of you have used induction for proving, but proving is what you have some sort of base case, right? And you make assumption something is true, and you assume, say, n case n is true, and it does not help proving n plus 1 case, right?
Yes.
Yes, and if it does, it's done, right? You won, basically, right? Of course, there's some other ways. You can say, okay, assume it's n minus 1, and you prove it for n, right? Does it show anything for n? Same thing, exactly the same thing. Or you can say, if it's n, if you assume n is true, does it help prove n minus 1? Then you don't even need the base, because you go down to 1, case 1, possibly. But there's some interesting, of course, gotchas there too, right? So you have to hold true for all n. But, okay, so prove by induction. We can look at this induction example, right? So, we assume the n, right, this case, right? And basically you add c in here, right? Basically it's cubed, right? So it's some c cubed, basically, right? Because again, you don't have to cube the c, so n to the 3, n to n, half the n cubed, right? You put the c inside, right? Basically, again, you can do. Okay, so what's happening here, basically? You might be asking, what is 4 on the 2? Basically, well, we can remember we have complete freedom for c, right? So we can just get rid of these 4 and 2, right? Basically, you can leave it like this, right? Basically, we are trying to prove, right, that, right, this, right, so basically we transform this recurrence into this type of mathematical form, right, and hopefully you can agree at some moment, right, we want this part here, okay, I can't, okay, this part here, right, oh, come on, this is this slide, we want this to be less than that, right, and that's our residual or difference, right, and well, we just need to pick a large enough c, right, remember, or remember my amazing graph, right, at some moment, right, somewhere here, right, up here, this is where the magic happens, right, so here, right, so tick, 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 this would be c equals 200, for example, right, right, this is where it happens eventually, right, so you say, okay, if you take c at least 200, right, you put 200 here, right, so then this is going to be, or recurrence is going to be less than the desired Cn cubed, right, basically. So that means, okay, it's big O, or complexity is O cubed, right? And yeah, so you could do this, and but I think it's relatively ugly, right? Because first of all, what's the biggest weakness of this method? You have to know the solution, sort of, right? I mean, what good is it? And again, you guess here cube, and so you think that's the tight bound? Is this like the best answer we can get? But do you think? If I'm asking, probably not, right?
Yeah.
Yeah, it's not, right? And the thing is, the example continues, right? So example continues, and it's not tight, right? So the thing is, you can prove also n squared, which is going to be better, right? So, but the problem is that it's not as easy to prove. And that's a real deal breaker in my mind, right? You have to find not only C, you have to basically to prove this, right? This MIT professor, right? Basically, you can pick another C, add another C constant, like a sub constant, right? And it looks kind of a little bit iffy in my mind, basically. Right? I mean, yeah, no, it's correct, mathematically correct, of course, right? But intuitively, right? If we had to do this every time we had some sort of recurrence, I think we go pretty crazy. We spend like, 20, 30 minutes, doing inductive proofs, right? Maybe more. No, we're not going to do it. So that's it. So that was like how we would do it if you didn't have master method. But now we move to to arrive at this master method. We'll look at the recursion tree method, the second approach, and this is kind of my favorite, right? Basically, it's a model. It's for guessing. On this one, I would recommend, if you have no idea what's going on sometimes, right? If there's something really fancy, again, to get an idea of what's happening, right? It's maybe not completely reliable, but I like it because it promotes intuition, right? I think in this part, intuition is more important. I believe it was not me, it was Einstein who said it, I believe, right? Intuition is more important than knowledge, but yeah, here, getting the feel for it, right? Again, intuition can be wrong, but oftentimes it is good. So, let's look at the recursion tree. So we have this recurrence. So what are we saying here? We have original problem of size n, right? So, to solve it, what do? What do we do?
We make a guess.
Well, we are going to be guessing afterwards for complexity, but assume this is like a recursive call.
N is 1.
So, yeah. So basically, we have this recurrence. So what does it mean? We have a size, n. Let's say it's 100, right? So the means is for each problem, we start with problem size 100, right? We're going to solve the problem for size 25 and for size 20 or 50, but that's not all. Also, we're going to make 100 square 10,000 units of work, right? For at that particular time, right? So, is this going to eventually end?
And
Is this okay? Is this a good recurrence? That's the question. Is this actually solvable? What do you think?
yes.
Yeah, of course, it is solvable again because it keeps going down. When you look at these recurrences, if these are going less than 1, right? N, right? It keeps decreasing, right? Eventually, you run out of n stops at 1, right? That's it. No more units. Nothing to do, right? You're less than 1, basically, right? So basically, eventually you run out of work. And the question is, how quickly do you run out of work, right? Well, n divided by 4, n divided by 2. Well, just quickly. I mean, it's like a really loose term.
Logarithm based.
Yeah, it's something. Look, okay, and that's intuitive first. But the thing is, what makes things. So, what do you think complexity of this? If you're not seeing these slides, like, what did you think complexity of this is? Well, thing is, okay, what do you think is like the best case scenario? Like omega, for example. Like, what could be possibly the best case scenario?
1.
Well, the thing is, look at this part here, right? So, hello.
Good morning.
Good morning. So, even if we ignore these recursive calls, like these recurrences, right? Even if we ignore these, right? No matter what, we have to do n square work, right? In this particular case, right? So you have to pay attention. This is at the level of, like, when we make, I guess I'll have to draw at some point, right? So, I'll make the slides work. So we have to do n square work, meaning, maybe 2 loops or something like that, right? Maybe 2 nested loops, something like that is happening. So this means that the best case scenario is going to be n squared, right? Ignoring recurrences. So that's already said, okay, it could be maybe more, it could be n cubed, could be n to the 4th, maybe n squared log n possibly, right? But this part, right, potentially, this could be very important. But what could be surprising maybe to you guys is that it might be also kind of say this might be more important, basically. We have like a fight. We have a fight. Which part is more important, or are they equally important? Are these recurrences important, right? Or is this more important? So let's do this tree, right? So first level, these n, right? So how much work do we have to do? We substitute n, and we do n squared units of work, right? Upper level, right? Now, we make recursive calls, n divided by 4, n divided by 2, right? And again, as you imagine, for each of these levels, what happens here? How much work will we have to do? Well,
n divided by 4
yeah, exactly. No matter what happens here, right? So same goes for here, right? And let's look at here. So n divided by 4 squared, n divided by 2 squared more, and we go to n divided by 16 because divided by 4 divided by 4, and here divided by 4 divided by 2, right? Here divided by 2 divided by 4 divided by 2 divided by 2. Are you guys with me so far?
Yeah.
Yeah, okay. Because let me know if something's not clear. So, and again, as you can imagine, here too, we have to square it and again make more calls. Alright. So, again, we need to know how much this is going to actually be, how much extra work this is going to be. Because remember, we started with n squared, right? Is this going to make our lives miserable, or is this actually maybe not so important? Maybe we'll see. We'll see. Let's continue. I think we get one more slide because I don't know how to draw it. Right. So yeah, n divided by square. Right. Eventually, we all of these recurrences, right, will run out to 1 because nothing, stops at some point. Right. No matter how large number you start with, right, it will go down, 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 down. Right.
Yes.
Yeah. So we don't know where exactly, right? Because we don't know what n, right? N could be, if n is 4, right? It's very quick, right? We don't even need that far, right? If n is 2000, you'll probably get few levels. But also you can see it's the 3, right? It drops down pretty quickly, right?
Yeah.
Right? Because divided by 4, well, divided by 2, right? And this seems like it's not too important, but it is certainly, divided by half, right? By half, by half, by half. That smells like logarithmic, right? Smells logarithmic. Should be, right? So I think we'll get to the full n, right? So let's count these levels. So here we do how much work? N squared, no question about it. So how much here? How much work is in this level? This is just a little basic math. So this is what, 1 to the 16th, right?
Yeah.
And this is 1 to the 4th, right?
Yes.
So together,
5/16.
yes, very good, excellent. So 5/16, indeed. We get 5/16, right? Okay, so what do you think? Okay, so first of all, you can guess or maybe try to do math here, right? But how much work will be here? We add up all of these four expressions. So this is what, 256, right?
Likely, yeah.
Yeah, because this is 2
Yeah.
to the 4th, 2 to the 4th, right? 2 to the 8th, 1,
Yeah.
2 to the 6. Okay, this is what? 1.
64.
Yes, this is 1,
64.
and this is
116.
16. Okay, so what do you think? What's the lower? What do you call it? Denominator? And what's the name in English? I keep remembering. Sky ties, south ties, sky ties.
Denominator and numerator.
Numerator. So denominator is what? What's the lowest?
256.
How much?
256.
Yeah, 256. Right. That's what it is. So on how many of them? So it's 1 to the 6, 4 256, right?
Yeah.
4 over 256, right?
Yeah.
4 over 256 on 16 over 256, right? You agree?
Yeah.
Yeah.
It would be 25.
Yes, 25 to 56. Hopefully you see what's happening here, right? You see what's happening, right?
How do we get the numerator?
Because we start with the worst one, the 256 here, right?
Yeah.
Yes, and then the rest have to be adjusted, right? Yeah, right? Like we did in 7th grade, right? And then you have to match them, right? In this case, easy because they're all. I wish I could. I think I can draw on this one, right? Let me see here. Where's my painter? Painter. Animations. Design. Oh, design. Let me do. No. Which one? Insert.
Apparently not.
No, there was a way to draw. I know I could draw. Here. Oh, there you go. I forget now. Where was the way? Drawing. Can I draw? I want to draw something. Oh, I want just a pencil. How can you get pencil on PowerPoint? I could do this, right? Oh yeah, I'll get pencil something, right? So, yeah. Oh no, that's not pencil. I know. I've done this before. But okay. But yeah. But hopefully you're. So 126, right? Right. I guess I'll do it on the table, right? So 256, right? And you have 164, right? 164, right, and 1/16, right? Right?
Yes.
You guys, so 256, right? 4, 256, right? 4 256, right? On 16 256, right? You know, 16, 16, right? I don't know how it's, again, right? And here you have 4, right? By 4, right? Up both sides by 4, here by 16, right? This is just a 7th grade, right? So, and it is 225, 256, right? Hopefully, right? So what does that smell like? So that's what I'm trying to get at. What does this smell like? Do you think? But okay, no. So let's make a prediction. We're not going to calculate, but what do you think the next step will be? What will be the number here?
125.
Yes, over 4096, I believe, right? Because it's power of 2, so like times 6, yeah. So times 16 times 16 times 16, right? So, no, we have n, right? We have n squared. We have n squared, not n squared, right? At each level, but also we have this number here, right?
Yes.
And the question is, we have to decide what is going to be the sum of this, all of this, right? And what do you think? Again, this is like, I don't know, maybe 10th grade math, right? What does this smell like? This number, this progression. What kind of progression is it?
Exponential?
No.
No.
I believe it's geometric, right?
Yeah.
It smells like geometric progression to me, right? Right? Because you multiply. Next number is multiplied by something, right?
Yes.
Yeah, you remember it's on the exam, right? On the high school exam, right? So this is basically the geometric series, right? And here, okay, well, so if you remember, there is a formula actually for this, right? And I don't remember it exactly, right? But intuitively, right? These units, these numbers, right? The second part grows very quickly, right? So means each next one, right? We're not even going to get to 2 here, right? We start with 1, right? We have to sum all of these up, right? Because always we do n square work on something, right? So the point of this is, right? This actually is some number, I think less than 2, certainly less than 10, certainly less than 2, right? We can find out exactly what this actually. We'll look at the formula in a moment, right? But doesn't matter. The whole point is this is a constant. It could be 5,000 for all we care. Well, we care if it's an actual real algorithm we want to use, but in general, right, in analysis, we don't care. And here, basically, these turns out in this particular case, the only thing that's really important is the fact that at each level we do n squared work, right? So the recurrence, these recursive calls, they go down very quickly, meaning they peter out. When I say peter out, meaning they just sort of like fizzle out, basically, right? It's not important as far as complexity goes, basically. So in this case, actually it's written as theta, but basically at least O, of course, when you say theta, I can say omega on big O as well, right? Theta includes both of them, right? So I can say it's O n squared, right? And that's the actual tight answer, right? This is the correct answer. I mean, the most useful answer, right? Right. So, and this is appendix, yeah. So we can calculate. This is, yeah. If it's, this is formula, right? If it's x plus x, right? No, the geometric series, right? Which one was which one? This one here, right? Right. If x is less than 1, yeah. Okay, yeah. We keep multiplying. So in this case, x is what? 5/16, right? Yeah, 5/16. So the answer would be 1 minus 5/16, which is 11/16 reverse. But yeah, 5/16. 11. So it's 16/11, right? So 16. So the whole progression. Okay. So the whole answer here would be where were we, right? Here, right? This part here is including the 1. It's 16/11, less than 2, like I said. All right. So yeah.
Another question.
Yes.
Would the coefficient still be insignificant if it was like if it would total up to 100 or 1000?
No, like I said, if it's fixed number, then it's still insignificant, right? If it's, that's still not important. Even if it's 5 million, right? It's important if you're doing some real work, actually, of course, and they say, yeah, it's 5,000, and you probably you don't want to use this algorithm for like maybe for small numbers, right?
Yeah.
But as far as complexity analysis, it's still same. 5,000 or 2 or 1611s, as in this case, right? Same thing as far as complexity. And that's why, again, because this is again, we try and get a feel for the algorithm, basically. That's what it is all about, right? So, but the thing is, out of this, and in this particular instance, it's not clear, maybe immediately, that what good are these recurrences. It turns out they could be very important, because in this case we had the actual work being done being the most important part, right? This recursive tree was not important as far as complexity goes, right? It just sort of like the extra work basically fizzled out, basically, right? It was some amount. It was of course some amount of work, right? More than one, right? This is like extra. Came out to be like maybe 11, 16, so yeah, so like 16 11, so like 3 11s extra or something like that. A little bit extra work, but not that much, basically. Okay, so on this substitution, right? We will get to actually to master method. Well, basically, somebody, I don't know when it was like 50s, 60s, somebody said, okay, they start doing these trees, I guess, for analysis. And they said, okay, but I think we can cover the basic cases. So you don't have to do this over and over and over, basically. So they came up with this master method. So basically, master method works for specific recurrences, right? For recursions. Again, recurrences in a mathematical term, recursions that we programmers use for coding, right? Very similar terms. Okay, so if you have this type of formula, right? Something like this in general, right? So you have a original, right? So you're defined in some sub form, right? You do some work. You have a function which does work. It could be x, could be x squared, could be x cubed, it could be x factorial, right? Well, then you don't really, then you say x factorial and go home, right? And then, most importantly, you have a and b, right? So first of all, a crucial part is that b is over 1, right? Why? It has to be over 1, right? If it's 1,
otherwise it will grow.
Yeah, it will grow, meaning it will be forever loop. Basically, you do work forever, basically, right? It has to go less, right? It has to be decreasing, right? So n divided by something has to be, so the new n should be less, right? Here, a has to be over 1, and I forget if it's exactly why was you have to be 1 or at least 1, right? You have to do at least 1 recurrence. Again, so that makes the formula useful actually here in this case. And then, turns out you have 3 basic cases. Yeah. So this is the only formula in this class. It will be on midterm also, right? You have to do like maybe one exercise. It's not that hard actually, right? We'll do practice after the break. It will be like 2 minutes. We'll take a break in about a couple minutes. So that's it. So this is where it applies for, right? So now we'll get to the idea, and then we'll get to actual formula. So this is the form, right? And again, let's go back to this one here. So you do some work at this level, right? Fn, right? That's the form. That's right. We had the right Fn. We had to do Fn. In our example, it was x squared, right? Work. So then, at each level, right? We do n divided by b pieces of work. Well, we have count n to b 8 times, right? 8 times, right? Because we get 8, right? On eventually, right? We should stop. And that's basic. This shows how it is proved. Again, you don't have to prove it yourself, but basically this shows how it was derived, basically. It's not really that hard. Just understand. Basically, the a and b basically end up with log a log b n, basically, right? How many leaves you get, basically, right? So eventually you have n to the log base b of a, basically, turns out, right? Work, right? So these are the levels, right? So height, log bn, right? And the actual work you do, right? So the thing is that so you have to decide basically this master theorem will let you know whether these leaves are the most important Are they equally important, or is this actual work being done is most important, right? So that's the idea. So you have three cases. I'm going to do this after the break. But so basically, you have this compare the function which does the work, right? X squared in our case, right? For some constant, basically, is it actually over? Let's take a look here, right? Minus epsilon. Epsilon has to be over. You find some epsilon constant, right? Epsilons are constants, right? Epsilon is typically small, but they could be also, in this case, could be pretty large, right? But it has to be over 1, right? This means that the function is not important. It's the trees which is important, right? We have not seen this case yet, right? So let's look. We don't have an example, right? So basically, the weight increases geometrically, right? So it turns out basically this part here turns out is not important. The increase in operations is more important actually. There's a second case, right? And this is probably the hardest case when it's exactly even, meaning the work being done on the leaves, right? They grow a similar case. So you need to consider both. The formula considers both, basically, right? We'll look at the example. Now it's a little bit abstract, right? Because you have a log k plus 1. This is the hardest case, right? I usually like to give the hardest case on a midterm, right? But it's not that when we start doing the exercise, you'll see it's not nothing too difficult. And finally, right, and this is what we saw, this is the second case, right? And it grows. And third case is what we saw actually in our example, right? That basically, this is what we had, right? You see, this is the easiest one. Meaning recurrences are not important, right? This is the easy case. You see, basically you find a positive epsilon basically over log base BA, right? N log BA plus epsilon, right? And means that the function is more important than this growth, right? And hopefully look at this. Okay, so let's look at this example. So that might be before we go to break. Okay, so we have an example like this. For t, right? So for each call, you do n work, right? At each level, you do n work, right? Linear work, right? Just one loop, possibly, right? And we make four calls to recursive calls with n's divided by half, right? And this seems like a big number, right? Right? But turns out, actually, here, let's take a look, right? So a is 4. This is a. B is 2, right? B is over 2. So first of all, you have to check, are they both over 1? Yes, they are. Then you do calculate. So n log base BA is how much? B is 2, A is 4. That is what? Log base 2 out of 4 is, of course, 2, right?
Yes.
So n squared, and we compare this with this, right? So you see, okay, and this is, again, remember, this is mathematically defined, but intuitively it's very easy, right? You see here, okay, this is smaller than that. That's all it's saying, right? So that is case 1. This means these recursive calls are more important than the work being done at each level, right? So it is going to be n squared, or we have our leaf growth, it's going to be n squared actually, right? Because you can make 4 calls of half size, right? So that's actually going to be defined, right? And the actual n here is not important. It seems maybe a little bit counterintuitive. I mean, how it's not important? Well, it's because the growth of these recursive calls is more important. But if you go to the next example, right? And this is a tricky one. Even though it's the case is relatively simple, right? You have n squared here, and as we just saw, the recurrence is still the same, right? So again, n squared. So both sides are equally important. So, but it's not n. So this is where people will go astray. They think it's n squared. It's not n squared because this means that we have some logarithmic growth from the leaves. We're doing n squared work, but we have also the leaf growth. And actually, it turns out then it is n squared log n, right? In this particular case, right? We assume basically there's it's a case that n squared log n, of course, log n basically k is 0, right? There's nothing here, right? Right. Log that comes out to be what? So basically, the answer is n squared log n. On the third one, which we saw, the last one, right? Right. This one here. So you have n cube, right? And this particular case, this is easy. This particular part, n squared, right? Plus epsilon, right? Positive epsilon, in this case epsilon 1, right? So basically this part here is less than this. Answer is easy. This is the easiest one, right? It's n squared, right? Finally, and this is the one, is basically you see something strange like this. This is like n squared divided by log n. Well, the good news is you don't have to worry about master method because it does not apply. I don't know how you solve this, right? Because it oscillates. There's some oscillations, right? You can't really say anything good about this one, right? So not solvable by master method. All right. So far, I think it's maybe intuitively you can have some idea, but we'll spend the next part of lecture solving these recurrences, right? You'll see them in action. It's pretty easy. You can do them, knock them out of the park immediately. All right. So short break. No, not short break. Let's do 15-minute break. Yeah.